Hello, everyone. I'm Gary Berman from Security Boulevard. It's a pleasure to welcome you to another great Security Boulevard webinar. Today, we're going to learn about protecting mobile apps and APIs from the inside out. But before we get to today's presentation, let's go over a few housekeeping items. As you see, we use the GoToWebinar system, so you'll see the control panel. Please take a moment to click on the questions icon and the little downward arrow. This webinar is designed to be highly interactive with our great speaker. We welcome your questions, comments, and suggestions in real time, and we'll get to as many as possible. If, however, we can't get to your question at the end of the presentation, we'll email the replies to you shortly. This webinar is being recorded, and the slides will be available to you on demand in a couple of hours. Additionally, we have a giveaway for $25 Amazon gift cards at the end of today's webinar, so stay tuned to see if you're one of today's lucky winners. And now, a special thank you to our sponsor for today's webinar, Paul Dent, VP of Product Management at Digitalai. Take it away, Paul.
Thank you, Gary. I appreciate that. And thanks, everyone, for joining today. We really appreciate your time. What we're hoping to talk about and that you'll hopefully take from this presentation today is a look at some of the security challenges that we're facing in the midst of the so-called digital transformation. Suddenly, organizations having to take certain business processes digital that maybe they hadn't before, and with haste, considering the global pandemic. So we're also going to look at solutions to some of those challenges and how they work. So to get us started, I'm going to give you just a quick introduction. As Gary said, my name's Paul Dent. I'm the Vice President of Security Product Management with Digitalai. I have been with the ArcFan organization, which came to Digitalai through acquisition earlier this year, for about 4 years. But previous to that, I've actually been researching software security for a little over 30 years. And that's one of the things I'd like to tell you about very quickly to give us a little bit of context for what we're going to be diving into. So my interest in this area actually began when I was around 9 years old. I had written a computer game that I was selling in school under the shareware model, for those that remember that. But basically, they could play a short demo, and for $5, I'd give them a code that they could type in and play the full game. And inevitably, one of the students came to school and told me that their parent had found this code in my software, which was not difficult, but just something I hadn't really been considering at 9 years old. And that really got me thinking about a number of things: copy protection, keeping secrets actually secret in software, and what we can do to achieve that. So ever since, I've been researching software security in a variety of ways, both theoretical as well as applied research, penetration testing, and essentially non-disclosed, low disclosure red team exercises with some really interesting facilities like hospitals, some other medical facilities, nuclear plants, tentpole movie sets, things that you would not really associate initially necessarily with hackers, but that amazingly can have a great impact. So with all of that said, let's go ahead and get started. And as Gary said, please, if you have any questions, type them out as they come up, and we'll make sure to get to as many as we can when we wrap up. Now, to set the stage and frame out what we're looking at today, particularly in the midst of digital transformation, but even before that, as we saw the advent of mobile, we see more and more complex client-side software that is running with a level of trust that's not necessarily warranted considering where the software is running, whether that's a web browser, mobile devices that we as software publishers have no visibility into, no control over, and even connected healthcare, connected auto, Internet of Things devices that are using the same types of technologies, the same communication frameworks, and again, running on devices that may not necessarily be trusted, that we may not necessarily know about. And of course, you can see that the challenge there is we're allowing these things essentially through our perimeter security mechanisms, web application firewalls, our firewall itself. We're opening ports. We are disabling or otherwise bypassing rule sets to make sure that these applications can communicate inbound with enterprise infrastructure. That communication today is mostly typically utilizing web APIs. And that's going to be a big part of another part of what we're going to be looking at today. So why are these apps at risk? That's one of the things that we need to fundamentally understand to solve the problem and understand the solutions and how they're going to solve these problems. When we look at distributed software overall, just like the example I gave in selling my computer game, even though it was on a floppy disk, much smaller distribution, the same basic principles apply to mobile applications, to JavaScript-based frameworks that are running in your web browser. This distributed software is inherently vulnerable, susceptible to reverse engineering or an attacker understanding how the application works and how it communicates with backend systems in hopes of compromising those systems, being able to forge what are seen as valid requests by the application. And then subsequently, the second challenge is software tampering. And that's where an attacker, through reverse engineering, has maybe identified a number of security controls in our software, modifies that software, and in a way that bypasses our controls, they're still able to run it in a modified version in a form, in a manner that the developers did not at all intend for. So if we keep those two challenges about distributed software in mind, one of the interesting things, we actually worked with the IT group on a commissioned security research project. And they looked at, as part of this research, they looked at 30 financial services applications available on Google Play. Of course, these are not identified applications by vendor, and ran those applications through a series of basic analysis and found some pretty interesting results. The first, we saw that 97% of these applications had no form of protection to prevent reverse engineering. As I described just a second ago, reverse engineering, allowing an attacker to, by using tools, even some manual analysis, understand how the software works. We can protect against that, but we're finding that most organizations today, even in apps that go out to public app stores, are not utilizing that type of protection. Now, kind of further to that, one of the things that's involved in reverse engineering, of course, is finding things that we actually intend to keep secret. That could be cryptographic keys, passwords, or tokens that allow us to communicate with back-end API systems. Remember, the systems that are essentially serving as the gateway between our client-side applications and the enterprise infrastructure housing all of our data. So they're pretty important. They're essential to the application working. They're also essential to keeping the data secure that's inside our enterprise infrastructure. If we fail in keeping that secure, if we have vulnerabilities in the APIs, even though they may not necessarily be directly exploitable, they may be exploitable by taking control of the application, reversing it, and tampering with it. And we're going to look at that in a bit more detail in just a minute. But getting back to this particular statistic, 25% of those applications I mentioned that were looked at had secrets embedded in them that allowed us to access APIs using keys or other secrets that were actually hard-coded into the software. Now, we've always learned as software engineers that hard-coding secrets into software is a bad idea, and generally that's true. However, when we have something like a mobile application that is, well, the mobile device is essentially, it's a computer, and it's running software that has its own mechanisms for utilizing hardware, utilizing memory, that sort of thing. We need to be able to carry out certain security operations like cryptographic operations and encryption and decryption of data to keep that information safe. If we're going to be doing any cryptographic operations, that's going to involve keys. So the point I'm making here is that eventually when we look at web applications that are a bit more complex running within the browser, utilizing web APIs on the back end, mobile applications as well, we need to be sure that the secrets that we may have to embed in software, and we may need to, We find plenty of cases, particularly in the cryptographic example, we need keys in order to carry those operations out. So 25% of applications revealing that sort of thing is frightening, especially when we consider that this is all based on very simple automated analysis. There was no manual analysis performed to look further in terms of pattern recognition and some of the other methodologies that attackers might employ to identify these secrets. So in reality, this 25% is probably significantly higher. The next that I want to review is about attacks against financial services organizations involving credential abuse. And what we typically mean by this is there's an attack against APIs, against applications in general that we refer to as credential stuffing. And the idea is that if I can understand how an application authenticates me as a user with my username and password, and I can repeat that, then in theory, I can execute as many of those calls to authenticate as the system will allow me, using stolen credentials likely found on the deeper dark web that have been mined from other data compromises, other data breaches that we've heard about in the media. All of those stolen usernames and passwords, they kind of just sit around in these large databases that get brokered and are very useful for these types of attacks, where we're actually automating authentication and determining of all of our stolen credentials, which ones are valid for this bank, which ones are valid for this electric company that allow me access to these individual accounts, excuse me. So of course, that list of enumerated valid credentials is extremely valuable, and the only intent may just to be to further sell those on as valid credentials. But nevertheless, what we are finding is 75% of attacks like that against financial services were targeting APIs as part of that overall attack. And what that really speaks to is the prevalence that we see organizations adopting web APIs for these purposes. So to get a little bit further into web APIs. Now remember, I mentioned earlier that essentially a web API is that broker in communication, but what you can also think of, and this is an API, application programming interface, much more generically. In software, when we write software, we write functions, and they're small units of code that do certain things. You can think of APIs as essentially calling functions, but in other software. And in the case of web APIs, we're calling functions in other software that happen to be somewhere else on the internet. It's extremely useful. It makes sense in terms of software engineering principles, but it also does present a new array of challenges that we haven't normally associated with, particularly web applications, when we're still very much focused on commodity attacks like cross-site scripting. This is a new set of challenges that we're finding not many organizations are necessarily ready to confront. Now, before we move on from APIs, it's also worth mentioning that one of the challenges that we see with securing APIs is a reliance upon client-side security. So that means if I am an attacker and I want to send an attack string, an attack payload of some sort to your API through your mobile application, I have to somehow trick your mobile application into allowing me to do that, whether that's modifying it, finding a bug, whatever the case might be. If we don't account for that on the API side and recheck that attacked payload, we're just going to process it like we would any other data that we receive. If we put all of the responsibility on the client side to sanitize that data, if you will, we will invariably see attacks successfully make their way through that application and to the API. And this probably sounds familiar to many of you. This is kind of another age-old software development best practice, that you don't rely strictly on client-side controls. But what we're talking about here is not just avoiding the reliance upon client-side controls, but also making sure those client-side controls can't be bypassed by an attacker by way of the things that we're discussing today. Now, when we consider those that a new array of security challenges involving APIs. What makes it really interesting is the rate at which APIs are being adopted. And this is driven by, you've likely heard the term microservices. It's, in my mind, microservices is an interesting sort of evolution, adaptation of what we used to refer to as service-oriented architecture. And the idea, of course, being just breaking our functionality, the problems that we're solving, down into much, much smaller manageable sizes, and our application can communicate and pull down just the things that it needs. So in contrast, contrasting what we saw coming out of the Web 2.0 era. So in 2014, according to the Akamai State of the Internet Security Report, and keeping in mind a lot of internet traffic moves through Akamai infrastructure, they have a pretty good handle on what that data looks like. And in 2014, around 54% of the traffic that they looked at was made up of HTML-based content, meaning that we're still seeing largely monolithic web applications where your web browser is almost serving as a dumb terminal, maybe a slightly smarter terminal, but it's still just presenting markup that the server has sent us based on a particular action that we took. So there wasn't really much of the idea of software running in your browser when we used to look at when we used to look at web applications. Now, 2018, a few years ago, 69% of that traffic moved to a type called JSON, which is JavaScript object notation, indicative of a very, very significant uptick in the usage of web APIs, because that's essentially the format, the language, if you will, that is used to exchange data between a client and an API server. So the point, of course, we're seeing these APIs leveraged more and more, but with these security challenges not quite addressed. API gateways, a technology that has kind of come about as we see organizations moving to cloud native applications, running things in containers that can be moved around, that can be ephemeral, but also providing an array of API endpoints or capabilities that our client-side applications can use. API gateways are great tools for managing and essentially brokering, as I mentioned before, calls into those various APIs that it's hosting. What it doesn't do very well is detect potential attacks based on application context. And that's really what we're talking about here. If an attacker has control over your mobile application and can now communicate with backend systems, there's a lot that attacker can potentially do that we didn't necessarily plan for as the publishers of that software. API gateways are not really helping us solve that problem. Web application firewalls, very similarly, although they are a true security technology, they solve other security problems. They're also not very useful in identifying these types of attacks where we have an attacker controlling your application. Now, threat scenarios in terms of how an attacker might carry out an attack of this nature can be really interesting. So we're going to look first at just a sample iOS application and what an attacker, the steps that the attacker will take to basically analyze the application, find the important parts, and disable them somehow. So let's take a look at that. Now, in this screenshot, we have this iOS application that we're going to be reversing, and we've loaded it into any number of common tools that fall into the classification of decompilers or disassemblers. And basically, these tools take a software binary, so in general terms, that could be our iOS app or our Android app, and reverse it back to something that is a bit more human readable than the native machine code that binary is most likely sitting in. And what this gives us is kind of a map of the software. It gives us the names of functions. It shows us various strings that might represent error messages to the user. With just those things alone and simple keyword searches, we can uncover quite a bit of interesting logic within the application. And in this next step, we've shown that we've identified the location in the software with a function called login user. We also identified a string that says username and password does not match. Now, tracing the usage of both of those artifacts, we're going to pretty quickly find exactly where in the code that true-false determination is being made. And something to keep in mind, most of the security controls that we might put into an application, like authentication, is the password valid or invalid. These things ultimately resolve to a true or false evaluation. So for an attacker, that's convenient because it typically means that when we go to modify an application, we're typically going to just switch a 0 to a 1 or vice versa to change that determination, and as a result, allow me to bypass a security control and gain access to the application or gain access to data that I'm not authorized to access. And in this particular example, we've run the software in a modified state, and it's now given us access to information on this target's mobile device that we should not have had access to. And of course, that translates to what we typically refer to as a BOR attack, break once, run everywhere, because this ability to modify can be automated into a patch and can be run against every version of every other instance of this particular application. The software is all the same. So an attack against one is valid against all of the others. And that's obviously not an optimal situation. Another quick example, this time looking at not just an Android application, but an actual Android application downloaded from Google Play. So in its form that would be presented to any other user that might download and have access to that application binary. And what we're showing in this screenshot is something very similar as to the example before, where we've reversed the software to an approximation, in this case, an approximation of Java source code that looks quite a bit like what the developer probably originally wrote. Now, this just has to do with the way these various platforms work, the way software is compiled, when it's compiled. But sometimes Java in particular, because of the way Java works, is reversed to, as I mentioned, a fairly accurate approximation of the original source code. So in this case, with this approximation, we do a keyword search for root, and we can pretty quickly find the area in the code that is looking to determine if this device is rooted. And for those that aren't familiar, rooted Android device, it's an analogy to a jailbroken iOS device. But what we really mean by both of those terms is that the device has been modified in a way that the security controls built into the operating system that, say, prevent one application from reading or writing memory of another application, one application from reading or writing data that is stored on the device belonging to another application. Any of those things any of these attacks that we're looking at today that we want to carry out, rooting or jailbreaking the device is most likely the first step. And so what follows, really, particularly on iOS, because jailbreaking iOS devices can be a bit more challenging, a bit more tedious than rooting Android devices. So what we really see is that in the case of iOS devices, a jailbroken device is most likely not one that we want running our application, depending, of course, on what our application does. But if there's any consequence to that application being hacked, so a financial services application is a great example, our flagship mobile banking application, we don't want that necessarily running on a rooted device because it leaves it vulnerable to malware. That, of course, malware on Android devices is fairly common, more common than we see on iOS. But in both scenarios, it gives whoever is controlling that device and your application by way of that device is able to do essentially whatever they would like. They can pull your application binary, any data that's stored on the device, off of the device for analysis. And that is typically what leads to additional attacks that eventually bring us to back-end systems where we've either identified a vulnerability within the API implementation itself, or even a vulnerability through the application, through impersonation, that gives us access to data that we're not authorized to access, the game over scenario. So with that said, what we're showing here is that in that reverse of the application, the Java source code that makes up this application, it took about 30 seconds to find this code that looks to determine if the application is running on a rooted device or not. Checking to see if a device is rooted is pretty straightforward, as you can see in this little snippet of code. So when we look at security controls like this, only part of it is the control actually working effectively and accurately in determining that the device is rooted. The other part of the security control is that it needs to not be identifiable by the attacker so that the attacker can bypass it. And we're going to look at exactly how we address that in just a second. So the approach that's recommended for addressing these types of attacks, these types of exposures that our mobile applications and web applications see today, there are three aspects to the recommended approach. The first is layered adaptive protection that addresses largely what we've been talking about, the susceptibility to reverse engineering and tampering that we see in any sort of distributed software. But another element is threat monitoring and analytics, basically visibility into what is happening. In the enterprise, we have achieved quite a bit of visibility in terms of IT operations, security operations, being able to analyze logs and other event data to actually alert us when something is down or when we think something may have been compromised or otherwise impacted in a security context. But when we have users download our flagship mobile banking software onto their device, that's where our ability to monitor completely ends. We don't have any visibility into that device, what's on the device, who's using the device, and we don't have any visibility into how our software is being used. So if someone attempts to, let's say, debug the application, which is a pretty common dynamic analysis mechanism that an attacker would use to basically just step through code, watching values in memory change, and eventually lining up code with functionality. Very similar to what we looked at, just a bit more of a challenging way to do it. But that and other dynamic attack mechanisms could be going on, and we would have no idea. And even if we have mechanisms built into the software to prevent it, we still aren't necessarily aware of it where we should be. We can almost consider our mobile applications that are running on devices that we don't know about, extended endpoints in a sense that do warrant a level of monitoring and not necessarily control, but protection. And then, of course, all of that must be achieved using existing DevSecOps processes, existing CI/CD build pipelines that we can rapidly integrate into. When we assume that those pipelines are in place in most scenarios in these applications, if we're adding additional tools, additional phases to that process, we have to ensure that it's simple to integrate and that it's not disruptive to release flows, to developer workflows, anything that may potentially introduce delay. So let's first look at the layered adaptive protection, the first aspect of our approach. Remember, we talked about reverse engineering and tampering, ultimately resulting in an attacker understanding how your app works to the point where he or she could potentially modify the app to bypass controls, security controls in particular, make it do things that we as the developers did not anticipate it doing, which can in many cases lead to a variety of security scenarios. Bugs, in many cases, software bugs can manifest as security problems. That's something that we are well aware of. So the key to preventing an attacker from understanding the app really comes down to both making it difficult for the attacker to understand, as well as making it difficult for tools to produce meaningful output for the attacker. So the example that we talked about before with a decompiler or a disassembler, there are ways that we can instrument software such that when those tools go to work in trying to reverse it, they encounter things they're not ready for and produce either garbage output, or in some cases they'll outright crash because of the unexpected processing situations that they're running into based on the instrumentation. So that's one key part of it. And we refer to a lot of those methodologies as various forms of obfuscation. So you can think of obfuscating an application, doing things like renaming our functions and our other identifiers, so that if we do find an attacker reverses our app, we're not instantly giving away what every function does. Now, of course, this is a post-build, post-development process, as you would imagine. And this is a really great point to make as well, that the issues we're addressing here, I've said a couple of times, they're inherent to distributed software. They're also not issues that developers are going to be able to address. We want developers to write clear and concise code. So if we are writing code for a security function, we should not try to obfuscate the names of those functions, because it just becomes difficult to maintain and manage that code. Nevertheless, we don't want our software going out there with those function names intact. And that's where this step in the process becomes so critical. We can apply things like renaming. We can do other things to the software that make an attacker, make it very difficult for an attacker to understand the flow, what function calls what function. And if you think about it, that can be very advantageous to an attacker as well, in being able just to see a diagram of a function calling into another function, which may branch into two different functions based on a condition. All of that can help to inform an attacker just even a little bit more to make additional progress in reversing the application. So if we can obfuscate that, make it nearly impossible for the attacker to understand, we're that much further ahead in preventing attacks against our applications. Now, the other piece of that, we've addressed the reverse engineering aspect, but now what about tampering? What about the ability for an attacker to modify an app? And that doesn't necessarily mean patching it on the disk and then running it. There are also ways to dynamically modify an application as it's running. A very common tool for that purpose is called Frida. It's a dynamic instrumentation tool and works essentially across every major software platform that we have, the mobile platforms, the desktop platforms. It targets a specific application, a process, and injects a JavaScript interpreter into that process. And what that allows us to do is in real time, while the application is running, execute JavaScript commands in the context of that application. So if I've examined it a bit in a decompiler and I have certain function names that I'm interested in, let's say function names that are maybe called encrypt file and decrypt file, using dynamic instrumentation, I can watch as that encrypt and decrypt operation carries out, and Frida can actually show me the values as it's happening, which means Frida can likely show me the cryptographic key that's being used in those crypto operations. That, again, is another sort of game over scenario. If an attacker now has private cryptographic keys or a private cryptographic key, the next step, of course, is building some type of offline decryptor, some sort of an oracle in some scenarios if we don't have the key necessarily. But nevertheless, crypto, as I mentioned before, can be very risky on rather within this sort of distributed software context. So we need active protection as well that looks for those types of attacks and prevents them, but also lets us know about them. So in the active protection stance, what we're really doing is instrumenting the application with small units of code that would carry these security controls out. Debug detection, I mentioned before how valuable debugging can be to an attacker. If we build into the app the ability to detect and prevent debugging from working, and then obfuscate that code so the attacker can't find it, we basically have just a big jumble of code as far as the attacker is concerned that is carrying all of these things out in a way that is no longer identifiable for an attacker. The attacker can't make a determination, cannot tell the difference between code that's carrying out security controls and code that's responsible for user interface updates or any other part of the application. What we also recommend in terms of app protection is a specialized type of obfuscation and dynamic protection that is targeted specifically at protecting cryptographic processes. So when we look at crypto in particular, there are going to be really two key attacks we have to be concerned about. Identifying our crypto key or keys in the application and lifting it, and then identifying the crypto code itself and lifting that out of the application. With those two things, I now have my little decryption tool. I can start stealing devices off of tables in Starbucks and mining credentials by decrypting them when they are actually stored on the local device, which credentials are cached quite a bit on the local device. So key and data protection is meant to address those two challenges. When we do have to integrate or otherwise build cryptographic keys into our applications, our client-side software, we can build in a mechanism that essentially transforms that key into a non-standard format that attackers will not recognize, that does not mathematically reverse back to the original private cryptographic key, the classical form, as we refer to it. And of course, that's essential. If you're familiar with hashing functions, one-way mathematical functions, this is very similar to that. The transformed key, and we call that white box, the white box key cannot be mathematically reversed back to the original key. And that's essential. It means that your private key will never appear in client-side software, even in memory. When the cryptographic operation is occurring, that key is never presented in its classical form. The second piece, of course, is providing more complex cryptographic operations, still in line with standard standard algorithm implementation, AES, the various forms of SHA, but mathematically much more complex, still certifiable, FIPS 140-2, compliant, but much harder for an attacker to identify within the binary. So that code lifting attack is also going to be close to impossible. Just like the rest of our security controls, that cryptographic code is completely mixed in with the rest of the application code. So now, even if an attacker were to find that white box form key without the corresponding code that goes with it, it's useless. You could, in theory, publish those white box keys on the internet, and without the corresponding cryptographic code that's been hidden within your application, that key is of no use. It won't work with any other cryptographic libraries. So when we bring all of those three things together, and as you can imagine, all of this is really working in concert, we have a hardened application that is able to respond to dynamic attacks in a variety of ways. You can see that the black rectangles here that are noted as guards, these are the runtime mechanisms, just examples that we might build in. Checksum in this case is an integrity validation, so that when an attacker does attempt to modify an application, the software itself has been enabled with the ability to detect that it's running in a modified state and either shut down, send a message out to some sort of back-end server system, which we're about to talk about. But nevertheless, we have an application that is self-defending to dynamic forms of analysis and attacks, we don't have to worry nearly as much about the susceptibility to reverse engineering and tampering when both of those are non-options essentially for attackers with this sort of protection. Now, I talked about the importance of visibility before, and this is where we can utilize what our instrumented applications are seeing in real time when we see every attempt to run our application on a compromised device, a rooted or jailbroken mobile device. Even though we may not want to crash the application, depending on what it does, a mobile banking app to kind of continue that example, if we crashed every time we saw the app running on a rooted Android device, we would get a lot of low ratings in the App Store, and we would probably get a massive increase in calls into tech support, not understanding why the app is crashing. So what that allows us to do really is factor in the business impact as when we formulate the security response that's appropriate. So in the case of running on a rooted Android device, maybe we don't crash the application because it would impact our user experience too negatively. But we can use a platform, we call this platform AppAware, to identify those scenarios in real time and orchestrate using them. So that could be the addition of a particular device identifier or a particular user account to a list that warrants some additional scrutiny when monitoring, whether that's utilizing something like a SIEM, Security Information and Event Management System. A lot of organizations bring this type of data into a SIEM to correlate with other data sources, other known data points, and that ultimately allows them to continue to reduce the noise that our security operations center sees, our incident analysts are seeing, and let us target alerting to very specific security use cases that we're actually concerned about. Very much like what we see being done with SIEM systems in the enterprise, where we align certain events to, say, identify a malware infection that is of consequence, as opposed to one that warrants just a re-imaging of the system. So again, that visibility is what provides us with the capability to respond server side as well as client side to these types of attacks. And as I mentioned, when we look at the need for rapidly integrating into existing processes with the understanding that we cannot impact schedules, we cannot impact release flows, all of those delays amount to losses. So in an effort to avoid that disruption, we have to ensure that these capabilities that we've talked about, these various mechanisms for protection, that instrumentation can occur with no disruption to existing systems. So we're really talking about a concept that we see referred to as security as code, where this process, this step in building protection into our mobile application can essentially be just another step in an automated pipeline that developers don't necessarily have to rely upon other groups within the organization to make changes. We don't have to rely upon systems being stood up. All of that can work in the security as code context. Another aspect, of course, is basically the ability to function in an agile manner, agility, being able to, based on this real-time information that we're gathering, consider how it impacts the protection of the application, the security of the application, and evolve that protection to what we're seeing in terms of real-time attacks. We have seen actually one really great quick anecdote, an organization that I work with that actually is a digital distributor for college textbooks for students and instructors, the campus bookstore essentially, but online. A lot of responsibility there, of course, in keeping that content safe. They are not the owners of that content. Those are obviously the book publishers. So in utilizing this protection that we've talked about in an automated fashion and bringing visibility through the app-aware capability, we were actually able to help them identify a campaign of FRIDA attacks. I described FRIDA, the dynamic instrumentation tool, earlier, against their systems, basically against their client-side applications, and that was allowing them to lift cryptographic keys, of course, which leads to the fraudulent unauthorized access to certain titles that can then be pulled down page by page through API automation and built into one PDF that can then be sold on the black market. So very serious business impacts in that particular case. And using this capability, we were able to identify that campaign of attacks before it became widespread. The key was recycled, and the protection was adjusted to prevent that type of attack. So to summarize here, the message that we're really speaking to is that this critical step in instrumenting this protection into an application has to be introduced in a non-disruptive manner. And that's the offering that we're providing. Now, this particular chart is a bit busy. So the overall message that we're trying to present here is that using all of the capabilities that we've talked about, we're able to build out an ecosystem of client-side applications and server-side APIs with the security challenges that we've described today addressed using, of course, the protection mechanisms that I've talked through with client-side applications, preventing reverse engineering, preventing tampering, but also the cryptographic capabilities that I described, where we can actually carry out cryptographic operations securely on the client side without concern that an attacker can identify those keys and lift them. We can utilize that level of trust, if you will, to then carry out basically shared secret authentication using secure crypto and granting access to those APIs based on that successful communication. Of course, the benefit here is that any application that attempts to call our APIs, even a testing tool like Postman, where we have the URL and maybe we have a token, if that call can't be carried out in a manner similar to what we're showing in this diagram here, where there's an actual shared secret that relies upon cryptographic, basically crypto encryption and decryption on both sides being carried out securely. And if that's not the case, we just simply reject the API request. And so what we're providing here is a robust solution against impersonation attacks. Nothing but your legitimate client-side applications can communicate with your API endpoints. All other requests are tossed aside because it's clear that they are not valid, since it wasn't in the context of an exchange similar to this one. And of course, what makes that critical, again, is the protection on the client side that prevents attackers from being able to peek into the app while these crypto operations are occurring, prevent the attacker from being able to see anything useful that might allow them to impersonate the application. So with all of those vectors cut off, they have very few options on the client side to leverage attacks. And then, of course, with this in place on the server side, only our genuine client-side apps can communicate. So we've effectively gated our APIs off from would-be attackers that are attempting to impersonate or otherwise forge requests to your APIs. Then talk very quickly as to why our customers trust us, why enterprises trust us to protect their applications, and speak very quickly as well to the Digitalai platform. So if you're not familiar with ArcSan, we were acquired earlier this year by Digitalai, as I mentioned, and we are known for our in-app protection mechanisms that we just talked about today. So in the Digital.ai world, we are a key part of the overall value stream management process. Essentially the ability to build software in the midst of digital transformation the right way, gather the data necessary to measure things in the right way, and all that time ensuring that security is being addressed throughout the entire life cycle. That when we first move into design phases, we are considering security scenarios, we're performing threat modeling, all the way through to pre-deploy, where we instrument applications in the ways that I described today to protect against reverse engineering, to protect against tampering. And then, of course, other aspects of this platform provide other capabilities like automated testing, automated release orchestration, and that is essentially, again, a platform that allows us to move software, move digital products through that pipeline in a secure fashion.
Paul, are you ready to address a few questions, or did you want to amplify something before we got to questions?
Gary, let's go ahead and answer some questions.
Well, first of all, I mean, thank you so much. That's incredibly interesting and relevant now that, so many people are just living their lives on mobile devices. What's your just knee-jerk kind of reaction to this convergence of work and home and school and, all on these mobile devices and through apps? I mean, are people just sitting ducks now?
In a sense, for sure. It is, as we see in the context of digital transformation, organizations moving to mobile applications, more modern cloud native web applications, there's a lot that needs to be done that we just don't really have time to do in bringing things to market in the time necessary for our current circumstances.
Yeah, no, that's for sure. And maybe you can share with our audience your perspective on DevSecOps and trying to get developers and engineers to kind of play nice with the security team. How do you do that?
Sure. That's a great question. And we know that traditionally security is often seen as what introduces delays and what is going to present problems for getting something to market. And what we advocate, of course, adopting a DevSecOps model is very important to being able to solve that challenge. And it really means, just as we've seen with aspects of infrastructure and utilizing infrastructure as code, where a development team that is pushing an update, pushing a new product through the pipeline, rather than waiting on external parties for systems to be stood up, databases to be created, it can all essentially be scripted as infrastructure as code. We're doing something very similarly with security. So while the security group can still do what they do, reviewing architecture, threat modeling, carrying out those exercises that make sure we're paying attention to security, the developers won't find themselves hindered by these steps being introduced to further protect the application.
Well said. Paul, earlier you spoke about some interesting use cases for your solution pertaining primarily in the financial services sector. Does your team focus on a particular sector, or is it just across all verticals?
We really do work across all verticals. Financial services is a big part of our business, particularly in Europe. We have GDPR, and they have to take a lot of those privacy concerns very seriously. Our software and technology really enables organizations and financial services to comply with that. But we work across quite a few verticals. We have a couple of connected healthcare customers that are using our software to protect the logic and the applications that are running on watchOS, and in some cases even proprietary medical devices that are implantable.
Indeed. And what is, in your opinion, the most common type of attack in APIs? Is it ransomware, identity theft? What are you seeing?
Sure. So there are really two pieces to it. The attacks against apps, the attacks against APIs, they begin as analysis, really, ways that the attacker can understand how the client-side application works, how the server-side APIs work. So if we can forge requests to the back-end API and monitor how it responds, very similar to other security mechanisms for testing. We send random information, we look at the response, we adjust what we send and continue to monitor that response. And eventually we're going to find, hopefully, a security vulnerability. So it really comes down to utilizing the susceptibility to reverse engineering and tampering, to understand how to call those APIs, and then utilizing problems within the API implementation. Probably a great example is a lack of or mismanaged authorization, where we may find some API endpoints are callable without the right authorization, just simply because of the implementation.
Indeed. And one of our audience members is asking, are you a security tool product or are you a service?
We are a security tool product. We do have a services organization, but we're primarily a security tool.
Mm-hmm. And what's the impact of building application protection into mobile app code, versus not? I mean, how big of a deal is it?
Sure. Well, I'll refer back to one of the examples that we looked at in an Android application. The difference between using this type of protection and not is really just how visible do you want the functionality of your application to be to literally anyone who's interested. And I'll also just a quick tidbit about why I think we're just now starting to really pay attention to this type of security challenges. When we built web applications in the Web 2.0 ages, the monolithic web server-based applications, we weren't concerned about client-side code security. It wasn't really there. We were more concerned about what someone could do targeting our server with cross-site scripting and SQL injection. Now with mobile applications, we're in a different situation, but to a lot of organizations that have been developing since the Web 2.0 days, it doesn't feel different. So we just kind of continue with our same development processes. We don't really worry about what an attacker could do with our software.
Right. Yeah. Well, we could just go on and on. Paul, this has been just fantastic. Thank you so much for sharing a little bit about what you're doing and your vision. And, you started at 9 years of age, so let's get those K through 12 defenders of the digital universe going. So thanks again.
Absolutely.
As I mentioned.
My pleasure. Thank you, Gary.
You're welcome. As I mentioned, we have 4 lucky winners for the Amazon gift card. They're Elvis M., Stephen L., Claudio A., and Rachel T. Someone from the Security Boulevard team will send you an email to confirm and to get the card over to you. And as I mentioned, this webinar is recorded and the slides will be available on demand in a couple of hours. So thank you so much for spending an hour of your valuable time with us. We truly appreciate that. We look forward to seeing you on the next Security Boulevard webinar. In the meantime, stay safe and be well.